Today we're going to finish chapter 4 by talking about the last thing in the chapter, which is centripetal acceleration and uniform circular motion. So let's talk about circular motion. So what do we mean by that? We mean, so this is something we haven't dealt with so far. Everything in this class has been moving in straight lines, or in the case of 2D kinematics, maybe something gets thrown in a parabolic arc. But we can have objects moving in circles, right? So we could imagine like a top-down view of a car driving around a circular track. And so this is our like top-down view of the car. Traditionally, these go counterclockwise, I guess. So the car follows some, counterclockwise path around this circle, right? So that would be circular motion around a circle, clockwise or counterclockwise, whatever. Uniform here, what this means is that the speed of the car is staying the same. Or the speed of the car is constant. This means, the person in the car is not like stepping on the gas and the brake and changing their speed. They're just, keeping the car going at the same speed all around, or, the speedometer of the car is staying at the same number on the dial, if you want to think of it that way. But as this car maintains the same speed, let's look at its velocity. I'm going to redraw this just a little bigger so we can see part of it. So here's like part of a circular arc. And let's look at a couple points on this circle. So let's say our car is right here. We know kind of from the definition of velocity that the velocity is going to be tangent to the path the car follows. So in other words, at this point, our velocity is going to be straight up because that's the tangent direction. So this is our velocity vector. I'm going to call this point A, and I'm going to call this velocity A just because we're going to look at another point right now. So at this point over here, we have a different vector because we're going in a different direction, right? So here, the vector that's tangent looks something like this. We'll call this point B, and this is our velocity B. Okay, so my question is the velocity changing, even though the speed is staying the same? The short answer is yes, because velocity is a vector. It has a magnitude and a direction, and even if the magnitude stays the same, if the direction changes, that is a change in the vector. If you don't quite believe that, we can actually show it on the picture. So I'm going to draw both VA and VB as vectors coming from a single point. So VA looks like this, and VB looks like that. So they're supposed to be the same length, but at a slightly different angle. So we know that we can add vectors by arranging them so they're like pointing head to tail. From that, and you don't have to know this, but just so you know what I'm about to do, that means subtracting vectors is the same as drawing a vector between the two heads of the vector. So in other words, something like this, that vector is equal to VA minus VB. Let me double check that. No, that's VB minus VA. That didn't take long to make a mistake. So we can draw a vector between them like this, and this vector is equal to VB minus VA. So what this means is that we have some delta V, right? We have some change in our velocity vector that we have drawn on this diagram. It turns out then for these points over here, for these 2 points, our delta V is in a direction to the left. And yeah, depending on what exactly these angles are, it might be a little bit down or a little bit up, but roughly speaking, over here, this delta V is to the left. Okay, let's do the same thing really quickly for a point up here at the top. So here, let's say VA is pointing like this, VB is pointing like this, and so VA, VB, VB minus VA is a vector pointing down. So our delta V here looks like that. This is B and this is A. So here, for these points up here, our delta V is pointing down. Okay, if we did this for more points around the circle, you would see very quickly that all of these delta V's are pointing towards the center of the circle. So all of the delta V's around this are all pointing into the center of the circle. Okay, so if all of our delta V's are inward, remember that our acceleration is equal to delta V over delta T, which means that the direction of delta V is the same as the direction of the acceleration, right? That's just a property of these vectors. If we have vectors on 2 sides of the equation, they both have to be pointing in the same direction. So if all of our delta V's are inward, that means all of our, well, first of all, we have a change in velocity that's happening over some amount of time, right? We're going from this point to this point. It takes some time for that to happen. So a delta V and a time means we are accelerating. I should start by saying that. So the existence of these delta V's means we have acceleration. Even though our speed is not changing, that's because our direction that we're moving in is changing. Okay, so if all of our delta V's are inward, all of our accelerations are also inward. And now we are ready to talk about this new idea. So when we have an object moving around a circular path, even if its speed is staying the same, it is undergoing acceleration. And this acceleration is centripetal. The word centripetal here means center pointing. So like pointing towards the center, which is just another way of saying in the inward direction, right? So centripetal acceleration really just means inward acceleration. Okay, so that's true of any motion on a circular path, and that's true even if we're going in the opposite direction. So if instead of going counterclockwise, we're going clockwise, all of our delta V's are still inward, all of our accelerations are still inward, everything is still pointing towards the center, it's centripetal. Okay, so we have an equation for how big this acceleration is, and we can derive it. It's probably not worth looking at where it comes from. We can just use it. And this acceleration, which we will call AC, our centripetal acceleration, it is equal to v squared over r. V is our velocity, or v squared is our speed squared. And r here is the radius of our circle. So we can say some things about this. The faster you are going, the bigger the acceleration is, and the smaller the circle for a particular speed, the bigger the acceleration is, or the bigger the circle at a particular speed, the smaller the acceleration. Okay, so this is our big important equation for motion around a circle. All of the circular motion we'll be discussing in this class is uniform. That is, it will be happening at a constant speed. So there is only one number to plug into this equation. You can look at stuff like this where your speed is changing, you're speeding up or slowing down as you go around the circle, and then you have to worry about some calculus stuff. So we're not going to worry about that. Okay, so whenever we have centripetal acceleration, whenever we have any acceleration, there must be a force causing our object to accelerate, right? This acceleration still obeys Newton's second law. Like for this acceleration to happen, we have to have a force. And if our acceleration is centripetal, we must have a net force in the centripetal direction. So whatever the circular motion is, there has to be a force pushing the object or pulling the object towards the center that is making it go like that. So this is, at the end of chapter 4 is kind of a deceptive place to put this, because chapter 4, it talks about springs and normal force and gravity, and these are all like different kinds of forces that we can see in everyday life. Our whatever force is causing this could be any one of those, right? Whatever force is centripetal pointing towards the center, that is not its own category among those, spring, string, normal force, etc. The centripetal force is one of those kinds of force, or another one we haven't learned about, like magnets or something, exerting a force on our object and causing it to move in this circle. Okay, so this attaching the word centripetal to stuff, all that is telling us is the direction. That's telling us the force or the acceleration is pointing towards the center of our circle. Okay, so some examples of this. We can draw some pictures, I guess. So we have our car going around the track, right? So if our car is following some circular path like this, there must be, if it is accelerating towards the center, there must be a force pushing it towards the center, or a net force pushing it towards the center. So what could that be in the case of the car? Well, forces on the car would be, gravity and normal force. Those are like acting in this direction, in and out of the board. That's definitely not inward. Turns out the only other force that's acting on the car is friction between the tires and the road. And in fact, it is that friction that is responsible for this inward force causing the car to go around the circle. The direction of that friction has to do with what way you point the tires. And of course, you need to turn the tires to go in this circle. So that's kind of what's going on here. We're not going to worry about the details of the friction interaction. The point is, the kind of force that is doing this is friction. It's something we already know. And also, this tells us another piece of information, which is if that friction goes away, you're not going to be able to maintain this circular motion. So if you're going around a circle and you hit a patch of ice in the road, your centripetal force, your inward force, is going to disappear. And when you get to this point, you are going to continue in a straight line and maybe crash into the wall of the racetrack or something like that. So that's why friction is important for cars being able to turn as well as speed up and slow down. Okay, so this is one example. Another example, and the demo I like to do in class, the slightly intimidating demo I like to do in class, is to I have a ball tied to a string, and I swing that above my head, which looks something like this. If I need longer arms for this. So I have some ball, and it's going in some big circle, around my head. So here, what force do we have? What forces do we have acting on the ball? So there's gravity pulling it down. That's not towards the center. The obvious thing that could be pulling it towards the center is this string, right? So it's actually the string tension. Let me draw a top view of this. It looks pretty much the same as the car. Here's our ball going around the circle. There's a string attached to it, and the force of tension from the string is always pointing towards the center because strings can only pull. And so in this case, our centripetal acceleration is due to a centripetal force that is tension. All right. In this case, we could do this with the car too, but since we're here, if we want to know how big this tension is, well, we know that the net force equals ma from Newton's second law. And we know this acceleration is centripetal towards the center. So this force must be pointing towards the center, and it has to be this big. So if we know how fast this is spinning around, we know the acceleration, this force is just equal to the mass times the acceleration. So for this example, that is just the tension. That's not, this equation is not generally true. It is just for a ball going in a circle on a string. Okay, awesome. There are other examples you can look at, roller coasters and stuff like that, but I think this gives you some idea of how to understand centripetal acceleration. Okay, there's one more thing I want to talk about, and that is the misconception isn't quite the right word, an often confused concept with centripetal acceleration, and that is the centrifugal force. And this is not something we have to worry about in this class. This is not something we're going to use in this class. I just want to explain this concept. So our centrifugal force, and what I mean by that is, let's take a step back. If you're in a car, and I'm going to draw this car bigger, and you're sitting in a car, and this car drives in a circle like that, you feel a force that like pushes you to the outside of that curve, right? It feels like something invisible is pushing you up against the right side of this car if you're making a left turn, right? Correct? So this is often referred to as the centrifugal force. This is how a centrifuge works. You spin something around and this extra force pushes stuff down to the bottom. It turns out the centrifugal force is not a real force in the way we have learned it. It is not from something actually acting on the object. It is kind of a illusion, we'll say, and I'll show you what I mean by that. Our car has these wheels with friction that are giving it this force that causes it to follow this path, right? So our car is feeling a force from the wheels that is inward, and that makes the car follow this path. You do not have wheels pushing you when you're in the car. You have the seat of the car and the seat belt and the walls. And when the car tries to turn, it is accelerating, right? It is changing its velocity. But you all obey Newton's first law, which is that unless you have a force acting on you, your velocity is going to stay the same. So in other words, down here, where your velocity is like this, you need a force on you to change your velocity. And, the car's tires, the friction can provide a lot of force to change the direction of the car, but it's harder to change your direction because there's not as much stuff touching you. So the result of that is that you try to go in a straight line. I drew this car at too much of an angle. We'll draw it turn just a tiny bit. You try to go in a straight line, which means in the car, as the car turns, you're going to end up, over here. So the centrifugal force is not exactly a force. It can feel like a force, but really what's happening is you are trying to keep going in a straight line and everything else is turning without you. So things we have to say about centrifugal force. Not a force. And it is because in the case of a car, it's because the car is turning without you, and you're trying to go straight. Try isn't the right word, but you obeying the laws of physics go straight. So the illusion is that you are getting pushed to the outside of the car. So like I said, we're not going to have to worry about this. I'm not going to ask any questions about it. This is just something that comes up anytime we talk about centripetal motion. I figured I would address this here.